Welcome to Geometry. My name is Steve Demme. I'll be your instructor, and we have an illustrious class here. Going to be with us for a couple days while we film these videos. But I hope that this whole experience will be a positive one, and one of the nice things that rhymes with positive or kind of matches is you can pause your DVD or your video as you're watching it. Now, we're going to give you a little introduction first, then we're going to jump right into lesson one. First of all, what you have, obviously, is you have a DVD. You also, hopefully, bought the instruction manual. Before you teach a lesson, or if you're an older student and you want to go through this all by yourself, watch the DVD, read the instruction manual, and what? Do it until you understand it. That means watching it a couple times or reading through it a couple times. Some people learn better by watching, some learn better by reading. But oftentimes there's things in the instruction manual that might not even be on the DVD and vice versa. So you need both of those components, all right? You watch it, you read until you understand it, and then you pull out the student book. And I'm going to show you that. You have the teacher book, should be like that, right? And then you have the student text, and the student text is going to have A, B, C, D, E, H for each lesson. So A and B are what we call lesson practice pages. Now these pages are just going to focus on the stuff that we're teaching in that particular lesson. Do you need to do both of those pages, yes or no? You don't know, and that's good because when I was in school you did every problem and every page and all of the practice problems. If you want to, fine. But those practice pages are for you to make sure that you've learned what you've watched and what you've read, and it gives you time to practice it. If you do the first page and you ace it, you don't have to do the second page. But if you need more practice, keep doing it. Once you've pretty much mastered the first two pages, then you've got D, E, and F, which we call, I say D, E, and F, C, D, and E. And C, D, and E are systematic review pages. So they're still going to focus a little bit on the new stuff that we just learned in that lesson, but then they're also going to focus on anything else that we've had up to that point. And in whether you're doing a lesson practice page or a systematic review page, the most important part, I think, are the word problems. So here's a question for you. Why do we learn math? So we can get good grades? So we can make lots of money? So you can do word problems. In other words, you learn so that you can apply it to real life situations. So the word problems in some ways are the key to this program. We want you to be able to look at a word problem, understand what's being asked, solve it, and then have the tools to solve it. All right? So how long will a lesson take? Well, we're going to do these videos in 2 days, and someone at home could watch these in about 5 or 6 hours, and you could learn the whole class in a day. Is that right? Maybe, if you're really smart. But most of us need time to assimilate it and practice it until we internalize it. So you might take a day or two in the lesson practice sheets, a couple days in systematic review pages. There is a test as well, separate test booklet, but that test, let me ask you another question. What are tests for? In an imperfect world, tests are to get good grades. But in a pure world, tests are to test for understanding. The only reason we have tests in this program is not so you can get a grade. It's so that you can tell whether you learned the stuff in the lesson practice and systematic review pages. So tests are tests in the pure sense, okay? You also have an H page. What do you think H stands for? We just had the printer call us the other day and they say, why do you have A, B, C, D, E, H? They thought we'd messed up our order. We didn't know the alphabet. H stands for honors. This used to be a separate book. Now it's included in this. And the honors is not going to be taught anything except in your student book. Now, the honors is for those that wanted more. We've had people say, I need more. I like math. I want to practice it more. Or maybe they have a math career ahead of them, or they're going to use it in engineering or some field of study. But the honors, you could do anytime. You don't necessarily have to do them at the end of lesson one, do the honors for lesson one. You could wait until you've done the whole book and go back and do the 30 honors lessons at a separate time, just to maybe review over the summer or before the next fall. But if you get to an honors page and you don't get it, don't be discouraged. Just say, well, maybe I'll just chew on it a little bit, do a couple more lessons, and then you might be lying in bed one night, oh, I get it. Do you think that'll ever happen? Yeah, you might call that a nightmare. I would call it a really happy dream. So Just work with the honors any way you can. They're enhancement, they're enrichment, they're a little bit extra for you, okay? Now, we're not going to use the manipulatives too much in this course. Manipulatives, that's a fancy word for blocks, the fraction overlays, inserts. We're going to use them a little bit. But you, all of you have pencil and paper in front of you, I hope, because when in doubt, draw. Geometry is a very visual subject. We're going to be drawing lines and planes and triangles, and we're going to be drawing shapes. And so use your pencil unless you have a really fertile imagination and you can visualize this all by yourself, all right? So use pencil and paper, use blocks. We're going to use a protractor a little bit, a compass. We've got straight edges. Anything it needs to help you to get it into your bean, okay? You know why we call this math, you see? Because oftentimes when you see it, then you see it. And that's what I'm really looking for, is I want you to understand it. So today and tomorrow, I want you to go, ah, when you get something, and that'll give me fresh energy and I can keep going, okay? Because that's what drives teachers. Teachers like to see that little light bulb go on. All right? Okay. Now, you've had years to learn stuff like addition and subtraction and multiplication and division, which you probably don't use those words unless you're in math class, right? I call that math vocabulary. And what about a factor? You know what a factor is? See? A factor is a math word. How about a divisor? Numerator. These are all math words. But as I was reading through and preparing for these, making this DVD, I noticed that you probably had a year to learn sum and adding and subtracting, and maybe another year with multiply and factors and product. You might learn 3 or 4 new words a year. Do you realize in geometry you're probably going to learn that many new words in the first lesson? And geometry is almost like a new language. There's lots of new symbols, there's lots of new vocabulary, and take your time with it. That's what I mean. You might learn this whole class in 6 hours watching the DVD, but to really internalize it, it might take you a while. So I don't know, how do you learn something? When you want to really learn what a word means, do you have it, you put it up on the bathroom wall? You put it on your placemat by where you eat? Whatever it takes, don't be discouraged by all these new terms. Just give yourself some time to assimilate it, and if you need to, try to use them in sentences. So say, Mom, I think that those 2 houses are congruent. Or, boy, I think that intersection just formed 2 vertical angles. They will think you're a nerd, but it's just okay, because try to use what you're learning in real life and look for examples in real life, because I really like geometry, because geometry is one of the most practical subjects. Algebra, you're learning a new language, you're learning X's and Y's and all that, but geometry, you will use geometry a lot, okay? So let's jump into geometry. Okay, first of all, if it was me, I'd want to know what the word meant. That's the way I am. So what do you think geometry comes from, the word? Well, you've got 2 things. You've got geo and you've got metry. And geo means ground, which is a part of the earth. Okay? So we're going to say earth or world. It's geo. So if you have geology, logy means study of the earth. Geography, what's graph? Right, that's maps of the earth, okay, or drawing the earth. But we have geometry, and metry means to measure. Okay, so it's the measure of the earth. So we're going to be studying geometry. This is from Greek, by the way, and later I'm going to draw some Greek letters for you. But we could do geo, and then I think it's metria, something like that. Okay, but you see the metric system comes from this word, metric, measure. I already gave you lots of examples for geo. All right, but geometry has been developed over a couple thousand years. And so the guys like Pythagoras and Archimedes and Descartes, remember Descartes, Descartes, he gave us the Cartesian coordinates. Pythagoras, we're going to study Pythagorean theorem. Archimedes, probably know him from Walt Disney, you know. He's that little owl. Isn't that Archimedes, the little owl in what's that one? Sword and Stone. Anyway. But Archimedes, these guys were scholars, and somebody took all the stuff that these scholars have observed over the years, and then they condensed it and they made a textbook for you. So it's important to learn what the scholars have observed. I don't know what word to use next, and or but. I use both of them. And it's important that you also learn to observe yourself. Or, but don't stop just memorizing what somebody else observed. Use your own brain and your imagination, okay? So that's what I mean about observations. These guys have observed this stuff, and then someone collated it, made a textbook of it, but that doesn't mean that we've stopped learning anything. You can still learn more about geometry and the earth around us yourself, okay? So these guys started off and they thought, well, what's the smallest unit we can start with? And so they decided to pick something called a point. Now, I'm going to draw this little point, but by definition, a point is so small that you can't see it. But then that wouldn't be a point, right? That's a picture of a point. That's what we call the graph of the point. But technically a point is, think of it like an atom. It's the smallest thing. Now you say, yeah, but you can see an atom if you have a big enough microscope. But just think of it as a point. We're doing some abstract thinking here. A point is the smallest thing. It doesn't have height, doesn't have length. You can't measure it because it's really small. But the way we do it is we say point, and then we put an A beside it to label it. So we're going to call that point A. All right? We usually use a capital letter to label a point. If you take a whole bunch of points and you put them in a line, then that, whoop, together you form a line. I already said it. In a line, we usually draw arrows on both ends. What do the arrows mean? That the line goes on and on and on. Now, lines can be curvy, but for our purposes in this class, we're going to be drawing straight lines most of the time, okay? Except when we draw a circle or an ellipse or a sphere. But for most of our situations, a line extends infinitely in both directions. How many points on a line? Not all at once. 10? Yeah, infinite. And how do you express infinite? Let's learn a new symbol. A sideways 8, right? Now, the way I like to think of it is if I keep tracing that, what do? Do I ever stop? No. So it's infinite. It's a sleeping 8. But there's an infinite number of points in here. But we need to at least label this and call it something. So we could call it line M, and we'd use a small letter. Or we could pick 2 points in the line, and we could call it by the points in the line. There's an infinite number of points, but we could say, well, this is RQ, and that would be line RQ. And the way we would write it is we'd put the R in the Q because 2 capital letters for the 2 points, just like the capital letter for the point. And then we put a little small line on top of it, okay? So that would be line RQ. Could it also be line QR? Does it make any difference? Not really, okay? But, you know, most of us are learning in an environment where you read from left to right, so we'd probably say line RQ. Okay. Somebody ought to keep track of how many times I say that today. Okay. So there's 2. Now we have something that some people call a half of a line. I'm not sure that's a real good definition because a half of infinity is still what? Infinity. But a line doesn't stop in either direction, but if it starts at a point and goes in one direction, what would that be? That would be a ray. And we do read a ray starting with the end point. We would say this was ray BC. Okay? Wouldn't be ray CB. That would be different. Okay? This is ray BC. Now, where do you ever use a ray in real life? What do you think of when you think of a ray? If you think of something that starts at a certain point and goes infinitely in one direction, what do you think of? I used to like to go out at night and turn my flashlight on and wonder if there was some guy up there in a spaceship or something that was going to all of a sudden see this little blink because as my little light beam went through space. Or does the light beam stop when I turn off the flashlight? You know, I think about things like that. But even better, how about a laser? A little laser beam. Now we're getting closer because a flashlight's got kind of a wide span. How thick is this? infinitesimally small. It's not thick, but it does have length, but it doesn't have a thickness. So a laser beam might be closer. And I think about, I wonder if there's laser beams still going off after I've been shooting them. And they're just going out, now they're bouncing off stars and the speed of light or something. Anyway, that's my strange mind. Okay, so think of it. How about a lightsaber? Unfortunately, they don't keep going though, do they? So they might be what we would call a line segment. They even make a fun, what's the noise of a lightsaber? Or something, okay. See, I get to make a fool of myself, you don't get recorded. All right. So we would call this line segment LM or ML, and we would put a little piece of a line on top of it, and that would be a line segment. Okay? Now, so far, how many new words have you learned? Well, you've learned ray, line, point. You've learned symbolism for a ray, line, point, and a line segment. You see what I mean about all the different stuff? So give yourself some time, read it, say it out loud, write it on your bathroom wall, on your mirror with some, non-permanent marker so that you can learn this. But now we're going to work on a symbol, and this symbol has given people trouble. So if you got any energy left in this first lesson, let's focus together here. What does this symbol mean right here? Equal. Now that's something that we know. Whenever we're going to talk about numbers or something that has a measurable number, I'm just helping you to get this straight, you use the equal sign. So if you say 3 feet equals 3 feet, right? You use the equal sign. But there's a new sign that we're going to use in geometry, and we're going to use it a lot. It's a combination of equal and this, which means similar. Now, similar means it's the same shape, but it doesn't have to be the exactly same measure. Can you think of something that has the exact same shape, but does not measure out to be the same number of numbers? I'll give you one right now. First of all, some of you today, when you came, were surprised to see how tall I was, correct? How tall do you think I am? 6.5 feet, pretty close. A little under 6'5", okay? But in that little camera that people are watching right now on their DVD screen, how big am I? Unless they have a really big television or are in a theater, I'm probably about this big, maybe this big, right? It's the same guy. It's the same shape, but it's a smaller size, right? Similar. Shapes can be similar. If I was able, with my to draw a perfect square, and then I draw another square, they have the same angles, all the sides are the same, all the sides are the same, same angles, but are they equal? They're not equal, but they're similar, okay? So shapes are the same. Maybe a picture of you would be similar to you, but not the exact same size, all right? Okay. Now, when you put together this symbol and you put the equal sign with it, you have something called congruent. Now, congruent means it's the same measure and it's the same shape, so it's identical. So you would say two squares that are the same size and same shape are congruent, right? Two angles that have the same measure are congruent. But it's got to be the same shape and the same measure. So we're going to say stuff like the measure of an angle. Whenever you see that little m, you think, oh, that's going to be equal, because that's going to be able to measure something. So equal is used with numbers. Congruent is used with shapes that are identical. All right? You say, that's not so tough. We get lots of questions on that. So that's one reason that we're going to focus on that a little bit. All right. So there's lesson 1. So now what are you going to do? Do a couple of the lesson practice pages until you get a hold of it. Read the teacher's manual. Then you're going to do systematic review pages until you say, okay, I got this. Take the test. You ace it. You go to the next lesson. What if you take the test and you don't get it very well? Then you go back and watch the DVD again, or read the instruction manual again, or work through your problems that you missed until you feel comfortable that you've got it, and then you go. Now, what if you're still stuck? You have lots of resources. You know where your resources are? Most of them are accessible online. Our website, we're always improving it. We live in a world today, more and more stuff on the internet, correct? Okay, so we have, maybe in the future we'll have more practice sheets for geometry. We have them up through pre-algebra now. Maybe there's an online support person you can call or email. We may even have a live chat someday. We've got forums on Yahoo. We have forums on our website. We've got games that we're creating that haven't come out yet. I'm just planting that seed right now, okay? So if you're still struggling, then call your rep, call us, go online, find some help, get some more resources, ask some questions, whatever it takes. But don't go to lesson 2 until you've mastered lesson 1, because I'm going to assume in lesson 2 that you have already learned everything there is to learn in lesson 1. You got that? That's huge. So how long does a lesson take? As long as you need. Okay. Okay, so a little quick review. What does this mean? Line segment AB. What's this mean? Ray AB. How about this one? Line AB. How about this one? Ah, a significant silence. If it doesn't have a symbol on top, it means the distance between A and B. All right? The distance between. I forgot to teach that a minute ago. So the students were just getting warmed up in lesson 1, and they weren't sure whether to ask questions or to respond. So now you're free, right? Now those people at home are saying, man, how can I get that guy's attention? Whew, it's okay. You represent them. So we're going to study now planes and sets and set notation. Now a plane, so far we've had a point which you can't measure, but it has location, right? It's a point. And then we took lots of points side by side, and that made a line. Now this is a little bit hard to think of, but if I could cover this board or this wall with lines, I mean I could just draw lines, 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 what would that make? A plane, a flat surface. A flat surface that moves, we usually draw it with a parallelogram, and we label it with a small letter, like this would be plane B. But in a sense, we should put arrows all the way around it, because a plane, like a line, goes in multiple directions, right? Infinite number of directions. But we're going to study just planes that lie, lines that lie on a plane, which is why we call this mostly plane geometry. Because you could have, let's pick my 10 bar here. You could have multiple lines all over this plane, right? But you could also have some that go through the board, right? Like arrows or something like that. But that would be in 3-dimensional space. Most of what we're going to be studying is in 2-dimensional space. It's on a flat surface. So where do you see planes around you right now? Tell me where you see a plane. Tabletop. Notebook. Your notebook. Wall. The wall. Okay, now where 2 planes intersect, what would that be? Like where this plane meets the floor. What do you call that all the way along there? That wall meets the floor. Where do they intersect? Corner. A corner, but that's a big, long, straight line. It's a line, isn't it? See, two lines intersect at a point. But 2 planes intersect, and they come together, and they form a line. Kind of interesting, right? What if you have 2 planes that don't intersect? Parallel. They'd be parallel planes. And can you give me an example in this room of parallel planes? 2 walls, ceiling and floor. Hopefully they don't intersect. If they do and we're in here, this will not be happy, right? Okay. And, okay, front and back walls don't intersect. Okay. So we've got planes, we've got lines, we've got points, and I'm just going to go ahead and finish it off. This is, you might say, 0 dimensions, right? This has length, so it's one-dimensional. A plane has length and width, so it's two-dimensional. And when we want to talk about three-dimensional, we can draw a cube because that's got length and width and depth or height or whatever you want to use. But they've got 3 different dimensions, okay? This 4 has 2 dimensions. This room has 3 dimensions, right? We're not going to talk about the 4th dimension. You know, Twilight Zone or anything. We're just going to talk about 3 dimensions. We're going to study a little bit of geometry and spheres and, you know, cones and stuff, but not much. Most of what we're going to be focusing on is 2-dimension, 1-dimension. Okay. So let's keep going now. If you have 2 lines that lie in the same plane, new vocabulary word, you have coplanar. If you have 2 points that lie on the same line, it's collinear, okay? But it's same. So same plane, coline, same line, coplanar, collinear. Whenever possible, we'll try to make these have a reason for them. If you're studying 3-dimensional, we talked about that being space, or sometimes it's called solid geometry. Now, sets. First of all, let's learn some symbols. This means intersect. It's in the opposite of, what's that one you think means? Unite, union. So this would be the union, and this would be intersect. Now, I don't know how your brains work. I'm just going to tell you how mine works. A union, you pull things together, right? A union, you pull them together. And intersect, I think of kind of like a croquet, what do you call it, wicket? That kind of comes down, and maybe there's something over here and something over here, and this clamps them, and it intersects them. Okay, so this is intersection, this is union. Another symbol would be empty set, or null, or nada, or there isn't one. For example, what's the intersection of 2 lines that are parallel? Nada, right? What would be the union of those 2 lines that are parallel? Those 2 lines that are parallel. So there's no intersection there, nada, but the union would just be the 2 lines because you just pull them together and that's what it would be, all right? So union, intersection, and if you have the U going this way, it means a subset of. So we could say, okay, how many people we have here at the 2 tables? We have 6 people at the 2 tables, right? So we would call this maybe, and you use these brackets for a set, we would say class. This is the set of the class. But the girls would be a subset of the class, wouldn't you? And the guys would be a subset of the class. What would be the intersection of the girls and the guys? There wouldn't be one, so we'll call that null. Empty set, right? What would be the union of the girls and the guys? Pull them all together. The class, exactly, okay? So you can use these kind of, I mean, you know, back when we were doing adding, we could have said 1 plus 2 equals 3, right? That gets tiring, doesn't it? So what we did was we decided to use an equal sign and a plus sign. We could say the same thing. We could say the guys are a subset of the class, the girls are a subset of the class, but we like to make things more efficient, a little bit tighter, and so we use symbolism, okay? Now let's pull together a little bit of some of these symbols, and I might have to use my spectacles here. This is what happens when you get what? Go ahead, let's all say it. Older. So we're going to draw two lines. And we're going to have these two lines intersect at this point, y. So here's a point x, here's a point y, here's a point z. Why do I put a line through my z's, do you think? Anybody? Or two. Because oftentimes when you start writing real fast, you just go, now is that 22 or z times z? So this is EZ. So that's a Z. That was a good laugh. I can keep telling jokes now. All right, so that's T, and this would be a W. Okay, so I'm going to ask you some questions to illustrate intersection and union. The union of line segment XY, and where's another pretty colored marker here? XY is a line segment. I'm going to draw this right here. XY. And line segment YZ. And it looks like I don't even have any of these. Okay. What's the union of those two line segments? So I would write it like this. I would say XY line segment, YZ line segment. What is the union of those two? What do you think? XZ, exactly. So you just say XZ line segment because this one plus this one, because the union combines them, puts them together, pulls them together. This and this makes this. What would be the, while we're at it, what would be the intersection of these 2 points? Where do they intersect? Yeah, point Y. So you would just say point Y. Now, you could almost tell me that, though, even without looking at the drawing. But again, when you don't understand what's written, draw it, because that'll help use more of your brain. You see the Y here and the Y here? You can almost tell me that they have a Y in common, right? So the intersection would just be point Y. Okay. Let's try this one. The union of ray TW and ray TY. TW and TY. Okay, first let's find them. Well, you look at it first. Now, at home, I'm going to do this several times today. When I ask a question on there, and I go like this, pause that machine, and then turn it off, think about it, and then turn it back on and see if you got the answer correct. That's one way. Now you guys, you can stop me right now, right? You can ask me questions. They can't do that when they're watching DVD. So the best thing they can do is use the pause button and say, figure it out, and then turn it back on and see if they got it right. That way they're not going to go, dormant in their brain. They're going to keep working with me here. So TW, let's draw it. Ray TW starts at T, the endpoint T, and goes this direction. TY starts at T, goes through Y, goes this direction. When you put those two together, what do you have? Line. How would you describe the line? Okay, WY. Any other way you could do it? YW. Is there another way you could do it? Or you could just do WT or TY or YT. As long as you pick 2 points, you're fine. All right? So you could say, what did you say first? WY. Okay? And you got it. Good job. All right? Again, what would be the intersection of those two? T, point T. All right? These rays, because they lie on the same line, what do you call two things that lie in the same line? Collinear, right, collinear. You pronounce it collinear, but I like to think of the line in there. All right, how about YT and TW? I already had that, should have left it there. Okay, and we're going to do the union of those two. The union of TW and YT. So the union of this and the union of this ray. Now this ray starts at Y and goes through T. So this one goes like this. This one goes like this. What's the union of those two? Exactly. Or you could just call it ray YT. Doesn't make any difference, but it's going to be the whole thing. We took a ray that started here and a ray that started here. We put them on top of each other. We united them, and now we have Y going through either T or W. Either one is fine. Okay? What's the intersection of line segment XY and TY? Line segment XY, line segment TY. What's the intersection of those two? Okay, so XY would be here, TY would be here. The intersection is point Y. Very good. I was tempted to say Y, but I gave in anyway. Okay, the intersection of YW and TV. The intersection of ray YW and ray TV. Well, we got television in this thing. Okay, there we go. What's the intersection of those two? Intersection, how do I do intersection? Okay. Okay, YW starts here and goes this direction. TV starts here and goes this direction. What's the intersection of those two? Line segment TY. From there to there. So it would be line segment TY. Very good. Okay, what about the intersection of ray TW and line segment XZ? Ray TW and line segment XZ. What's the intersection of those two? There is none. Well, how am I going to tell them at home with a symbol, though? That's right. There is none. So there is none. It's null set. It's void. There's nothing. Okay. And using subsets, could you say that XY is a subset of what? XY is a subset of what? You could say line segment XZ. You could say line XZ, right? Okay. How about TY? What's that a subset of? Line segment TY is a subset of, you know, I should say, show me 5 answers for this one. Because you could say, well, this is a subset of that line segment, or that line segment, or that line, or this ray, right? Lots of different options there. Is this helpful? Okay. If you have 2 lines in the same plane that intersect, if they're 2 lines, they have to be in the same plane. But if they're on a board, they're also on the same plane. If they intersect, the opening or the space between the 2 lines is called an angle. And to denote this, we often put little arcs to show that this would be angle 1, angle 3, angle 2, angle 4. All right? Generally, though, even though there are several angles up here, when we just draw one angle, we don't draw lines, we draw what? We could draw line segments, but we usually draw rays. What do you do if the rays run away from you? You catch some rays. That's an expression for getting sun. Anyway, you can laugh now. That was a joke. Okay, so where the 2 rays meet is called a vertex. What's the plural of vertex? Not vertexes. That sounds like a place down near Texas or the border. Vertices. Okay? But if we were going to talk about this, a ray has an endpoint and a point. They're going to share the same endpoint, so the shared endpoint would be called the vertex. So this would be D, E, F for our example. Now, we're going to put this little arc to denote that we're talking about this angle, because technically we could be talking about the bigger angle. We'll get to that later. But most of the time we're talking about the angle, but to make sure we put a little arc there to denote that. And then we usually use a Greek letter. Now in the book I chose alpha, which could be looking like a fish swimming against the current. But you could also have a beta, you could have a gamma, you could have a delta, you could have a phi, you could have theta. But these are popular angles that are used, or what we would call it, like a moniker, a name for an angle. We often use a Greek symbol. Okay, the way we would also describe this angle, we could say angle alpha, or we could say angle, and we draw the symbol for an angle, and we put EDF. Or we could call this angle FDE. What do you notice about the way the symbols are structured? Yes?
D is always in the middle.
The end point's always in the middle, because the angle either goes bump, 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 or bump, 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 but you got to have the D in the middle. You can switch the outsides if you want, but the D has to be in the middle, the end point, all right? Now, we're going to talk about now measuring angles. Now, if we have two angles that are identical, we would say they're the same shape, and we would use the word congruent, right? But if we're talking about the measure of an angle, what would we say? This is the hard part. Let's try it again. The measure in terms of degrees using numbers, it would be equal. Back to our good old friend equal. Okay? Congruent is the shape is identical, but the measures are the same. It would be equal. Now, how do you measure an angle? I mean, if you have, let's pretend these are lines. So we have this angle right here. I used to be a geometry teacher. The students would sometimes estimate the angle of my nose. This was good for my flesh, right? But if you were looking at the angle, this would be a small measure because we're only looking at the opening in here. This would be a little bit larger, a little bit larger. If it's all the way straight up and down like that, what would that be called? A right angle, or a 90-degree angle. Turns out that if you go all the way around, there's 360 degrees. And one of the things that you use to measure angles are protractors. Now, I brought two that I have in my desk at home. A little bit larger, a little bit smaller, for smaller angles. Little tip when you're using them, make sure most of these have hairlines that intersect, and it's not at the bottom of the protractor, it's up a little bit. You notice that? Or here it even has a little hole in the middle, which is up about 1/4 of an inch. Okay. But look what I have as a teacher. Gigantic protractor, okay? So let's measure this angle DEF right here. So I'm going to put this little point here at the end point, and I'm going to put the 0. Is there a 0? I don't see a 0, so where am I going to start? This says 170, 60. What in the world is that all about? Yeah, because it turns out if I start here, that is 10, 20, 30, 40, so this is 0. So I'm going to start using the smaller numbers to measure this direction. So I'm going to say 10, 20, 30, 40. Oh, goodness, I drew a 45-degree angle. So I would say that this is 45 degrees, or I would say the measure of angle alpha is equal to 45 degrees. If I use the word measure, I'm going to have numbers. It's going to be equal, right? But if I said angle alpha is congruent, let's say, to some angle beta, which I haven't even drawn yet, they're the same shape, same size, all the same, they're congruent. But the measure of these two angles would make it equal. Got that? Okay. Now, let's say that you don't have an angle. Let's say you want to create an angle. And this is where I hope, really, take some time. You can turn off your stuff. You can just get out your little protractor and your piece of paper and start drawing angles. So let's draw an angle. I'm going to start with an endpoint. I'm going to start with a straight line, and I want to draw an angle that is 50 degrees. So I put this here. Where do I mark it? Well, I don't start at the 170. I start at the 0, 10, 20, 30, 40, 50. Put a little point. Then I take my straight edge, either a ruler or I can use the side of the protractor, draw another ray. I could label it A, B, C. I could label it, what do you use? What kind of letters do you use in the middle here? Hebrew?
Greek.
Russian?
Greek.
Greek. Okay, Greek letters. All right. This is a piece of cake. This is not hard, is it? Okay. So angles. Angles have to measure the opening. We use the points on them to identify them, or we use a little arc, and we use a Greek letter inside. That's it. Now we're going to talk about more vocabulary to describe more kinds of angles. So you see people think math is just numbers, but there's a lot of verbalization, vocabulary, okay? So if you have an angle that is a measure of 90 degrees, which we already said this last time, many of us know this one. What kind of angle is this? It's a right angle. It's a square corner, and what we do is we put a little square there in the corner to indicate that that's a right angle. Now, I'll probably say this later. I don't want to forget. I'll say it now. Someday you're going to take a standardized test. You'll notice that the tests in your book are multiple choice, because we're trying to get you to think in terms of multiple choice answers, because that's mostly what you're going to see in a standardized ACT or SAT test, okay? But they will give you problems, and they will try to trick you. I don't know why, but they will try to trick you. And they will tell you things, and you'll look at it and you'll think, that should be a right angle. But unless they put that little square there, don't trust your eyes. Estimate with your eyes, but only trust what they give you, okay? That's a right angle. By the way, that's where the word rectangle comes from. Rect means right. So right angle, rectangle. Okay, now, what if you have an angle that is this? I have trouble with this one myself, because I think of an angle as something that's not straight, right? But this is called a straight angle. And the angle doesn't go from here to here. The angle goes from here all the way to here. Notice we always start here when we're measuring and move counterclockwise. So what do you think the measure of this angle would be? If it's 90 to here, how much more to here? Another 90. And what's 90 plus 90? 180. So that's a straight angle. Okay. Most of the angles that we're talking about are not straight angles, but we're going to learn that. We don't use that too much. Now, it's possible. Have you ever heard of somebody saying, I was driving my car in the snow and I did a 180? That means I was driving my car, I hit the brakes, hit the ice, and then I was going. So what does that mean? I didn't go completely around, but I went halfway around. So I used to be driving this direction all happy. Now I'm going here sweating profusely, okay? So that's called a 180. What do you call it if you pull a 360? Okay, that would be I'm driving, and then I go, and then I'm happy again, so I'm still going, and I haven't hit anything, okay? That's a 360. They used to talk about this with some famous basketball players. They could run down the court, dribbling, they would jump up, do a complete spin, and then dunk. That's awesome, right? You know what ice skaters can do, though? Now, that 360 would be because they go completely around the circle, right? I've seen some ice skaters do two complete, I don't know if you call it a revolution or rotation. How many degrees would they spin? Well, if one time around is 360, 2 times around would be 720. And now I think they're doing quads, which would be 4 times around. 1440. I should write a math program. Okay, so 3 times around, 4 times around, you multiply 360 times 1 times 2 times 3 times 4. All right. Most of the angles that we draw, though, are called cute. They're just cute. Because an acute, and that's what the word is, acute angle is, it's greater than 0, but it's less than 90. So this is 90. So it would be anywhere between this little bitty angle here and this big angle here. It's acute. All right? Most of the angles we're going to talk about are acute angles. If it's greater than 90, so that would be greater than 90 degrees, but less than 180 degrees, what do you call those guys? That would be like an angle like from here to here. It would be foom. How'd you learn that word obtuse? You must have had this class before. Nobody knows the word obtuse unless they're being obtuse. Okay, so obtuse, an obtuse angle. It's greater than 90, so it's like 91, 92, 93, 94, 95, but it's not quite a straight angle. All right? What do you think we haven't had yet? One more big angle. That's called an angle. Okay, what kind of angle is that? Well, it depends which way I'm going, right? Because if it's this, that would be obtuse. But if it's this all the way around, that's called a reflex angle. Reflex. That is greater than 180. So we'll write it in here. So it's greater than 180, but it's less than 360. Okay? So for example, our little, what angle is this right here? Acute. But what if I had gone like this? Reflex. Now, let's do a little math here. What if this was 50 degrees? What would this reflex angle be? How far? All the way around. 360. So you subtract 50. So this big boy would be 310. All right? You have to memorize the 180, the 360, the 90 because you're going to be using those a lot. And you can subtract back and forth. All right? That's it. Now, just one more tip, though, this reflex angle. How would you measure this guy? You got a couple ways you could do it. You could do this. Let's say this is 110 here. You subtract 110, and you get 250. Or you could say, well, if this is 110 and a straight angle would be 180, then this must be 70 because 70 plus 110 makes 180, right? Then you take the 180 up here, you add 70 to it, and you get 250. Because we don't have protractors that measure 250-degree angles. Okay, so you have to divide it up into smaller. Is that okay? Do you like this? Okay, so one more time. If the angles are congruent, how do I write it? Congruent. If the measures of the angles are the same, what do I do? Equal. Okay. All right. So we have a question from the back row. Go ahead.
Okay, so all angles, if the measure of the angle is equal, then the angle itself would be equal, so it wouldn't be congruent.
Okay. So if the measures of the angles are equal, aren't the angles congruent? See, you could never have two angles that are equal. Their measures could be equal, but the angles themselves would be congruent. So if they're congruent, they'll have equal measures, but they'll have congruent shapes. So you would never say angle 1 is equal to angle 2. You'd say angle 1 is congruent to angle 2. The measure of angle 1 is equal to the measure of angle 2.
So numbers can be equal, but shapes aren't.
Shapes are congruent, numbers are equal.
Okay.
Nice job. Okay, this next lesson we're going to play hang block. What do you think of my man there? Now you have to contribute here, but you've got 2 legs, 2 arms, 1 body, torso, and 2 pieces of his head. That's all you get. And then the guy, okay? So someone said he needs some hair, but I don't think so. Doesn't it look good without hair? Okay. So here we go. We're going to start off. Pick a letter. Go ahead. Oh, good letter. Okay? A. Go ahead. No, hurry up. This is video time. G. Ooh, that's a good one. I'm going to put the torso up first. Okay. G. M. Well, do you want a leg or an arm?
I'll do a leg.
Okay, there you go. Leg, okay. That was M. Go ahead.
C.
Okay, back to you. L. Okay, which one do you want?
A.
We already had A. Pick another letter.
B.
P.
Oh.
That was a good one. R. Oh, man, you guys won. Okay, so it's per,
You forgot the R.
pen.
I said R.
Oh, I'm sorry.
Oh.
Okay, perpendicular. Now, we're going to do one more, but we don't have time for hangman. So another word that is usually taught at the same time as perpendicular. I want you to at least be able to spell this word. See, it's P-E-R-P-E-N, perpendicular. So what's you talk about? Perpendicular lines and parallel. How do you spell parallel? This is hard. P-A-R-A-L-L. Yeah. Okay. That's how I think of it. Because it's got the 2 L's, 2 parallel lines are 2 lines that lie in the same plane that do not intersect, right? Their intersection is the null set or empty set. Okay. So we have perpendicular and parallel. And thank you, Mr. Blockman, for your help. Okay. See, you can use blocks for lots of things besides just math, can't you? Okay. So if we were to draw 2 lines in the same plane, and we'll put little points. This is point A, point B. This would be line AB. And then we draw another line maybe right near it, and we'll call it CD. And we say that these 2 lines are parallel, so we'd say line AB is parallel to line CD. Okay? This is how we would verbalize it. This is how we would write it. What's the intersection of these 2 lines? That's right. Null set, empty set, because they don't intersect. What would be some examples of parallel lines that you've ever seen? Railroad tracks. Now, technically, they're curvy, but there are 2 lines, hopefully, that just go straight. What else? Parallel lines. Lines on a road. Okay? I just got a motorcycle, and I heard, though, that in the winter, be careful, because sometimes those little painted lines can be slick. But those 2 lines are parallel. How about around the room? You see any parallel lines here? The ceiling? Drop ceiling? Yes? What else? Well, these 2 lines, but also the sides of the whiteboard. Yeah. What else? This is good. You're starting to learn. The lines on your notebook paper. Okay, parallel lines. The corners are parallel. Good. All right, what do you think perpendicular means? Perpendicular, we don't use the expression of parallel lines like we did for this. We say there are 2 lines that form a right angle, or 2 line segments that form a right angle, or 2 rays that form a right angle. We're going to put the right angle symbol there. That would make perpendicular lines. Give me an example of perpendicular lines. Outside the room first. Are telephone poles perpendicular? Before the storms. Okay, sometimes they become obtuse angles, but perpendicular, hopefully. Are these walls perpendicular? hopefully, so that they don't fall on us, okay? So walls are perpendicular, doorways are perpendicular, otherwise the door won't close. Have you ever had that? Okay, when the trim is down or something? Okay. You see how much you use geometry? I have worked in construction, and I've worked as a carpenter, I've been a painter, and you know, a lot of things are about making things square, making sure that things are perpendicular and walls are parallel, etc. Okay, now, if you have a line segment, and a line segment has, well, we would say it's got a definite length, right? And let's do this one, A, line segment A. Boy, without my glasses, I can hardly see. I think that's a G. And then we've got H in the middle here. What would be the point? This is a finite set of points. This is a segment. This is not a line. The exact middle point, what would we call it? The middle point. Reduce middle point to one word. Midpoint. Okay, this would be the midpoint. And there's a couple ways we could show that. We could say that the distance between AH is the same as the distance between H and G, right? Doesn't have a symbol, it's a distance between. So the distance between here and here. We could say that these two line segments are congruent, right? Because if they're the same length, they would be congruent shapes. Okay, this is a midpoint. What about if we had an angle and, you know, we cut this baby in half, didn't we? We cut it in half to find the midpoint. But let me draw an angle. How would you find the way to cut an angle in half? Let's say that we have an angle like this. We don't have a midpoint in the angle. What we do is if we cut an angle in half, we say that we bisect it, or two sections. Bi, two, tri, three, right? Bisect, two sections. See all this new vocabulary again? It is a lot, so just don't be overwhelmed by it. Just take your time, a little bit at a time. So if we have angle YHB, so this would be Y, this would be H, this would be B. Wonder why we chose B. Go ahead, tell me. B for bisect, okay. So this ray bisects this angle, and then we could say that angle YHB is congruent to angle MHB, right? Or we could say the measures of these two are equal. Measures are equal, angles are congruent, okay? But how would we construct one? How would we construct the bisector? How would we find a midpoint? I mean, what if you didn't have, let's go back to our little midpoint guy now. What if you have a line, segment, from here to here, and you want to find the midpoint and you don't have a ruler? What would you do? But you could estimate, but I want to find the exact middle point. What? Get a compass. What is a compass? Doesn't this tell you north, south, east, or west? Okay, this is a compass. Now this compass is usually much smaller. The kind that you would have are usually about like this, right? And a compass, it's funny, when I think of compass, I think of circles. Because I like this one because you can put this up very point there, put it in your paper on your desk, and you just turn this and spin it, and you make a circle, right? But the key to a compass is not the fact that it makes shapes. The key is that it maintains the same distance between here and here, okay? So people used to measure with things like this. They would like measure here, then they would measure here, 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 here. These were used for measuring. So a compass, here's what we're going to do. I'm going to take my compass here, get a good shape, and I'm going to use this white end as my pointy part, and I'm going to draw a line here, and I'm going to draw a line down here. Now I could draw the whole thing. Either one is fine. Then I take it over here, and I do the same thing again, and I draw here, and I maintain the same distance, and I draw here, and then what I do is I get my straight edge out here. And I'm going to connect these points. And there is my midpoint. Isn't that cool? Now, if it was me sitting there, I'd turn off that DVD player, I'd pull out my compass, and I would start bisecting line segments. It's fun. It's interesting to do, okay? By the way, this particular midpoint, this line, I mean, forms a right angle, doesn't it? So we could also say that this is a perpendicular bisector because it even bisects this angle, cuts the line in half. It's a perpendicular bisector, and we did it by forming it with the compass. But let's try another way. Let's just draw a regular bisector of an angle using our compass. Okay, so the first thing we're going to do is I'm going to draw an angle. Okay, I don't have a protractor. Because if I had a protractor, I could just put this thing up here and say, well, that looks like about 48 degrees. I'll just go up 24 and draw a line, right? Or I can pull out my trusty compass. And I'm going to put a line here. Hold it. And here. Then I'm going to take my compass out here to each of these points I just made and draw that and draw that. And then I get my little straight edge and I connect the point from here all the way through here. Oh, didn't draw it very well, did I? And so there is my bisector. Now, you know what I noticed, though, when I was practicing this couple of days ago? I looked at this, because we haven't had this yet, but I'll tell you anyway. If this is the same length, and this is the same length, and this is the same length, and this is the same length, we have even created a shape with 4 sides. And I'll tell you later what it is. Okay, think you can do that? So turn the machine off and practice bisecting angles, finding midpoints. Remember what a parallel line is and a perpendicular line. What did the acorn say to his dad when he grew up? Gee, I'm a tree. Delayed action. Okay, so we're still studying geometry now, but we even have 3 more words for vocabulary now. S, C, and A. And if we had time and if we had all kinds of fun, we would make hangman for these guys. But I'm just going to tell them to you. They are supplementary, complementary, and adjacent. I mean, you do use these, you know. You heard about the guy that walked into the little pub one time and the peanut said to him, man, you look good. Guy looked down and the bartender said, yeah, those are complimentary. You know, complimentary nuts. Okay. You're getting all the bad jokes in one lesson. Supplementary, we use supplement. Adjacent, the houses that live next door to each other are adjacent, okay? But now we're going to apply these to angles. Supplementary angles, complementary angles, and adjacent angles. So if I were to draw 2 lines intersecting in the same plane, I'm going to label these using what letters? What's this? Alpha. Beta. This is a little tougher because we don't, I mean, it looks like a B. It looks like an A, B. Gamma. You'd like to say gamma, A, B, C, but there's no C. It's gamma. Okay? And this must be a fish that's diving. And then you have kind of looks like a D. That's delta. Okay, alpha, beta, gamma, delta. So if we were going to use these, we could use those to describe the angles. So which angle is adjacent to angle B, beta? No. Delta would be opposite. Adjacent is touching, or they share the same side. So which is adjacent to angle beta? Alpha and gamma. Very good. What's adjacent to delta? Okay, what's adjacent to gamma? Beta. Okay, because they share the same side, these two are adjacent, share the same side, these two are adjacent, okay? All right. So now if we want to put in some points so we can be more specific here, we'll put Q, we'll put, these are too big, we'll put a little V in here, we'll put T, S, what do you think I'm missing up there? R. Okay. Now we still have these guys, they're kind of hiding in there now. This is beta, this is alpha. I'm laying the foundation for stuff we're going to do later, but only believe when you're doing a test or doing a book what they tell you, what is given. So what we're going to say is given line RT, and they usually write that given, RT and QS, these lines, they intersect at point V, all right? So we know that they are not two lines that are going like this. They are two lines in the same plane. They intersect at point V. That makes a difference. Now, you've got a couple different angles here. We know now that these are adjacent, these are adjacent, these are adjacent, these are adjacent. How many pairs of adjacent angles do we have up there? 4 pairs, right? Watch this. 2 angles that are opposite, like beta and delta, that form, what shape is that? What letter in the alphabet is this right here? That's a V. And what's this one right here? Down here. It's an upside down V. And you put these 2 V's together. And the reason I keep using V's is because these 2 angles that are opposite are called vertical angles. Now, I like to think of vertical as being straight up and down. But these 2 angles are also vertical. So alpha and gamma are vertical. Beta and delta are vertical. You have 2 pairs of vertical angles. See that? Okay. Vertical angles, do you think they have the same measure? Let's look at 2 angles here. Okay, right now at the top, let's say this is beta and this is delta. Are they small angles? As I continue to pull these lines closer and closer, they keep making the same, right? So vertical angles, the ones that make the V, the opposite angles are congruent. They have the same measure. Look at these 2 angles on the side when I'm doing this. What's happening there? They're getting smaller, they're getting larger. But whatever you do to one, you end up doing to the other when you have 2 straight lines intersect at the same point. You see that? So vertical angles are congruent. Now, can I prove that to you? I know that I can. Do you think it's true, though? Yes. We're going to use another word, postulate. Postulate. A postulate is something that even though we observe it's true, it looks true, we really think it's true, and if we measured 1,000,000 of these, we'd find out it's true, but we can't prove it, but we postulate it. So we're going to call it a postulate, all right? So we're going to use postulates later when we start doing postulates and axioms and other kind of stuff. Okay, let's do some more here. What if you have 2 angles? I think I'm getting kind of messy here, so let me erase this a little bit. I'm going to draw a big shape now. And I'm going to draw a whole bunch of numbers in here. So we're going to start with 1, 2, 3, 4, 5, 6. Now, this is given in the book that these 3 lines intersect. It's also given in the book that this line and this line are perpendicular, which means that they form right angles, okay? Now, let's just look at these angles here. Tell me, what angles are adjacent to angle 3? 4 and 2, they share the common side. Very good. What angle is a vertical angle or opposite angle 1? Angle 4. So if this is 30 degrees, what would this be measured? 30 degrees. They'd be the same. What angle is perpendicular? What angle is a right angle up there? 6 and 3. Good. Okay. If angle 5 was 70 degrees, what would angle 2 be? 70 degrees. What would angle 4 be? If this is 70 and this is 70, what would this be? How do you know it's 20? That's correct, but how would you know? Because 90 minus 70 is 20, because if this is perpendicular, that's perpendicular, that's perpendicular, that's perpendicular, right? So we know that these corners are all 90, so that if this is 20, this has got to be 20. How much is this? 90. This is how much? You knew, I gave you one angle and you told me all of them. Because you know that vertical angles are congruent, vertical angles are congruent. These add up to 90, so you can subtract from 90 to find this one. Very good. Okay. What do you call two angles that add up to 90 degrees? Complementary. I don't know how you want to think about this, but my old brain is before CDs. We actually had these things called cassettes, and the most popular cassette was called a C90. So that's how I think of it. Complementary, 90 degrees. Find your own way. Do something, okay? How about two angles? I mean, let's say that we didn't have this right here, and we had a very big angle here that was 110 degrees, okay? Two angles that make a straight line or make a straight angle, two adjacent angles that share the same size, that add up to 180 are called supplementary. Now, how would you think of that? What's going through your brain? How do you remember that? Well, you could think supplementary straight angle. They both have an S and they both make 180. Or, I thought of this way just the other day. You could think, well, two C's, 90 and 90 makes 180. I don't know. Use whatever, or just write it 50 times until you remember it. But supplementary make how much? 180. Complementary make 90. Okay. Let's just do one more little problem. We have this in the book. I'm going to give you one measure of an angle. You tell me the rest. So we've got this, and we've got this, and this is perpendicular, and this is 43 degrees. All right. Tell me the rest. Sure. Let's number them. This would be 1, 2. I don't even see a 3 in there unless that's. Yep. This is 4. This is 5. All right. Go ahead. Tell me 1, 2, 4, and 5.
5 is also 43 degrees.
Why would this also be 43? They're vertical angles because they make V's, right? That's how I think of it. You got two lines, two V's, vertical, vertical, right? All right, very good.
1 and 4 is 47.
How did you get 47 degrees?
Because 2 is 43 degrees and 1 plus 2 is 90 degrees.
So 1 plus 2 must be equal to 90, right?
Well, angle 1 and 2
Right?
are equal to 90 degrees. And since 2 is 43 degrees.
So if this is 43, then this must be 47 because you subtract 43 from 90. Very good. Okay, if that's 47, what's this one? 47. What's this one? 90. What if you had this one? What's 90 plus 47? 137. What kind of angles would those be? Supplementary. Okay, you're doing well. Okay. All we're doing is subtracting. We're using what we know about vertical angles. Complementary make 90, supplementary make 180. What do I have here? Describe it to me. I'm not going to look at the board. Parallel lines.
Two parallel lines with a line through them.
Two parallel lines with a line through them. What do you call that line that goes through them? You probably never guessed this one. I could probably win in Hangman on this one. This is called a transversal. Transversal. Now trans, you know, kind of cuts like transatlantic or trans-American ride or something. So this is a transcontinental. Okay. So it's a line that cuts across. So L is parallel to M, and then R intersects it at 2 points, which forms a whole bunch of angles. How would we describe these angles, though? We've got, how many angles we have there? 8 are named. So what we're going to say is that between the parallel lines, so from here to here, so how can we do this shading it? These are called interior angles. This is inside the parallel lines. What would you think you'd call these two lines then? I mean these angles, 1, 2, 7, and 8. Exterior angles. Okay, that's not tricky. I'll tell you when it gets tricky. Transversal's tricky. Okay, so 3, 4, 5, and 6 are inside the parallel lines. They're interior. 7, 8, 1, and 2 are outside. They're exterior angles. Okay, if, let's try our little, yes?
Shouldn't the letters designating the lines, shouldn't they be lowercase? There's capital R points in them.
There, they're lowercase. Very good. Nice job. Okay, that's good. I would have called that one T, but the guy that wrote the book put an R. I don't know why. All right. So these lines then make these angles. So we're going to say that this is 60 degrees. Angle 2 is 60 degrees. So tell me all the rest. What do you think?
8 is 60.
Well, before we go any further, we need to think about something. If you could visualize this, and I don't know how to do this in real life, but if I could pick up this line and this whole area here, just like from like right in there, and pick it up and put it right on top of this, would it be the same? Yeah. It would be. It would be identical. Because if you have a straight line cutting the, even though this shifted over, this 2, 4, 3, 1, if I pick that up and put it on top of this one, you wouldn't see any swervy lines or double lines. They would be identical, okay? So what we say is that angle 2 corresponds to angle 6. Yes?
It'd be easier to visualize the bottom line sliding up along the transversal.
Okay, so just take this and just slide it right up like that?
Yeah.
That's good. Thank you. Well, yeah, very good. So we can just slide. We don't have to pick anything up. We'll just slide it right up like that. Until these two lines are on top of each other. This is the same line, these two lines. Very good. Okay, so we say that these lines have created angles, and angle 2 and angle 6 starts with a C. Close. They correspond. They correspond. So, I mean, you could say upper right, upper left, lower right, lower left, lower left. You could say northeast, northwest, southeast, southwest, whatever you want. If I said, what's the southwest angle up at the top, what would you say? Which angle is southwest? That'd be 3. What's the southwest down here? 7. So if we slid these up, put them on top, 3 and 7 would be on top of each other, 1 and 5 would be on top, 2 and 6 would be on top, 4 and 8 would be on top, all right? These are corresponding angles. So now let's go back. If we know that these angles are the same, let's start drawing some deductions. If this is 60, this is a straight line, it makes 180, what would this be? 120. What would this be? How do you know so fast? Well, because they're vertical or because they're supplementary. What would this be? 60. All right, now let's move down here. If this is, what do you think this one is? Because these corresponding angles would be on top of each other, they'd be identical, this would be 60. If this is 60, what's this one? 60 vertical. What are these two? 120. Whew. All right, what else are you observing? I'm going to use some really big words now. You ready? If two parallel lines are cut by a transversal, alternate. What's alternate mean? Well, these are corresponding, right? But alternate means the opposite side. Like 3 and 6 would be alternate interior angles. This is an alternate interior because this opposite, okay? This would be a corresponding angle. This would be a vertical angle. Whew. So corresponding angles look to be congruent. Vertical angles we know are congruent, and it turns out because of what we know, alternate interior angles are congruent. Which angle is an alternate exterior angle? 8 and 1, okay, because they're both exterior and they alternate opposite sides. Which angle corresponds to angle 1? Okay, 1 and 5 correspond. So they're already congruent, vertical. So now we find that alternate exterior angles are congruent. Whew. So try one more time. You answer the sentence. I mean, you finish the sentence. If two parallel lines are cut by a transversal, corresponding angles are congruent. If two parallel lines are cut by a transversal, alternate interior angles are congruent. If two parallel lines are cut by a transversal, alternate exterior angles are congruent. But you see, we use what we knew from the previous lesson, we use what we learned, because of vertical angles, because of supplementary angles, right? We were able to deduce that alternate interior, alternate exterior angles are congruent. This is wonderful. But what did I start with? What was the given? What did I start? The very first thing I said. Two parallel lines, right? I told you that. I guaranteed you that L and M are parallel. Because you knew that, then you knew that all this other stuff was true. What if I came out here and I said, I don't know if those two lines are parallel. But if I found that all my corresponding angles were congruent, all my alternate interior, alternate exterior angles are congruent, I can go reverse. Except we don't say reverse in math. We say they make tennis shoes too. Converse. Okay? The converse is true. And this is real important in geometry. Because if all these angles are congruent, corresponding, alternate, then I can go and deduce if these are congruent, then they are parallel lines. And we call that the converse. Okay, this is real important. That make sense? Okay, so you know if they're parallel, this follows. If this follows, then they're parallel. That's the converse. Has anybody here been to the Grand Canyon? If you do, they talk about the North Rim and the South Rim. I don't know if you knew that. The South Rim is where most people go. The North Rim, not so much. It's a long drive around the Grand Canyon. But I like that word rim for this next unit because whenever you measure the distance around, let me think, what would be measure? That would be meter, right? Geometry, measure the earth, a meter. And what's around? Perimeter, distance around. And so whenever you measure the distance around, so this board, for example, is 3 feet by 4 feet. If I don't like this trim, let's say I want to put white marble around my board instead of golden oak. How many feet would I need? I just told you, come on. How many feet? It's 3 feet. The width is 4 feet. The height? Wake up. Lunch is coming. Huh? No, 3 plus 4 is 7, and 3 plus 4 is 7, and that's 14 feet. Okay, that would be the distance around the board. It's the rim. See the rim here? It's the rim around the edge. Where would you ever use perimeter in real life? Just give me some examples. Where do you ever measure the distance around? Okay, first. Okay, a yard, a fence. Very good. You have to measure the distance around. Hopefully you won't need to put a fence by the house. You just need 3 sides, right? Okay, that'd be the perimeter. This room is pretty brand new, actually. It's only been here about a month. We just put this floor stuff, like the little rubber stuff around the kick plate. I don't know what you call it. But we had to measure around the bottom of the room. How about that door back there? If you want to buy trim to put around the edges, probably about 7.5 feet high, and it's probably about 3.5 feet wide. So you have to measure your perimeter. Okay? Pardon? Trim for anything. Okay. So that's perimeter. Now, when we talk, this is probably review, but just in case it's not, make sure that perimeter you add up the distance around. Now we have several shapes. One of them I just mentioned a little bit before. What shape is this? Well, it's probably not perfect, but it's the best I can do to represent a square. How would you define a square? Describe it to me. 4 sides, 4 90-degree angles. Okay? So 4 sides and 4 90-degree angles. How about that? That's got 4 sides, and it's got... Oh, 4 equal sides and 4 right angles. Okay, that would be a square. What is this shape, now that we already have it up there? Rectangle comes from, what did I tell you already? Right angle. It's got 4 right angles, okay? But some people call it a stretched square, but the sides don't have to be the same. I'm going to ask you a tough question now that you're advanced students. Is a square a rectangle? Does it have 4 sides and then 4 right angles? Yes. Okay, a square is a rectangle. Is a rectangle a square? No, because it would have to be the same length, right, each of the sides. All right, so we know 2 shapes here, square, rectangle. How about this one? What do you know about that one? Well, if this side is parallel to this side and this side is parallel to this side, that would be called a parallelogram. Sounds like something you mail, but it's a parallelogram because parallel sides. By the way, are these sides parallel? Are these sides parallel? Are these parallelograms? Yes, but they have right angles. This doesn't have a right angle, okay? These are parallelograms. These are rectangles. See, we're stretching the gray matter in your brain, aren't we? This is good. This is good. Okay, what if the sides are the same? We like to put little lines through them. So this, I would put, these 2 sides are the same. These 2 sides are the same, right? But they're different than this, so I put 2 slashes. These 2 sides are the same. These 2 sides are the same. But what do you call it if all 4 sides are the same? A rhombus, right?
Yeah.
Maybe like a CD-ROM bus? I don't know. Anyway, okay. A rhombus is a parallelogram, but all 4 sides are the same. And that's what I drew with my compass before. I don't know if you remember that. I didn't know that. Just learned that this week. When I drew that, that was the same length, and then I put my thing here and here, made 2 more lines, right? Because my compass never changed, I really was drawing a rhombus, and that's how you could draw a rhombus. You could get out your little compass now and you draw this. Remember, you make the 2 lines, and you put your thing here, and you make your slashes here. And if you connect all the points, you get a rhombus. Okay? And we know from that these angles would be cut in half, don't we? We learned that, bisecting. We're learning all kinds of things. And maybe even Pythagoras didn't even know this. Okay. Oh, it's another bizarre shape. And this one, it's 2 parallel lines, see? But the lines, these are parallel, but these 2 sides aren't necessarily parallel, okay? Now, to understand this shape, I have to tell you a little story. Because what happens was, in the local zoo in Pennsylvania, we have a thing called a zoid. And the zoid escaped. Now, this zoid is from a remote part of a jungle way overseas. And so they had to call people that were native to that land and say, how do you catch a zoid? The zoid has escaped. We've tried everything. We have put food out. We've done all these different things. We don't know how to do it. And they said, what you do is you find a mountain, close as you can to being like a triangle, and you cut 2 parallel gashes into it and make like a tunnel that goes all the way through the mountain. And we're just doing a cross section here to look at it. And then you put your doors up here and leave it like that. And what happens was he'll think that he's to his native habitat. And that little zoid will go up there, and he'll go into his little place there, and these doors will shut on him. And that is how you trap a zoid. Oh! So that's why we call that one the trapezoid. Okay, so trapezoid is 2 parallel lines, and these are not necessarily parallel. Okay, do you like that? Okay, let's see if we covered everything. Oh no, we've got something else in this unit to do. So now you know about trapezoid, you know about rhombus, parallelogram, etc. Now, by the way, we're going to be doing area shortly after this lesson. And I want to do it at the same time so you get confused. But perimeter is just the distance around. So if this is 5 inches, and this is 6 inches, and this looks like maybe 6, 7 inches, and this might be 10 inches, what would the perimeter of this shape be? This is easy. You just add it up. What's 5 plus 7? 12 plus 10, 22 plus 6, 28 inches. But what you're going to see is, oftentimes in the book, you'll see something like this. And this is the height. And we're going to get into this in a future lesson. This is only there to confuse you. You need this when you're finding area. But don't add up the 4. Perimeter is only the edges around the outside. Okay? That's it. Period. But when you're finding area, you need the 4. When you're doing perimeter, you need the outside rim dimensions. Okay. A triangle. What's a triangle look like? 3 sides. You want to find the perimeter of a triangle. This is 9 feet. This is 8 feet. This is 12 feet. What's the perimeter?
Well, this is back on the trapezoid.
Okay.
Don't the 2 angled sides of the trapezoid have to be equal?
No. In fact, the trapezoid could be that.
Okay.
But it's got to have
The top and the bottom have to be
parallel, right? It's got 2 parallel sides, but those kind of like transversals can do any wee wall they want. Okay. Good question. Okay. One thing I don't know if you figured out yet, let's draw a right angle, and let's connect the points to make a triangle. How many degrees is this right here? 90 degrees. Now, if we were to continue this and put another triangle right up here and make sure that these is also 90 degrees, this is 90 degrees, what do you think the measure of these 2 angles is? 90. So I'll put a little arrow, that's 90. How about this one right here? That's 90. So how many degrees in a rectangle? The interior angles. This angle plus this angle plus this angle plus this angle, 360 degrees. Okay. What about a triangle, though? How'd you get 180? half of 360. But let's even say that this is 50 degrees and this is 40. And this is 50 over here and this is 40, right? Which we could do because parallel lines cut by transversal alternate interior. Ooh, we're using what we've learned already. But we know, regardless, these have to add up to 90. These have to add up to 90. So turns out 50 plus 40 plus 90. You're right. Rectangles are 180 degrees. I'm sorry, triangles. Ooh, thank you for catching me before everybody had a heart attack at home. Okay, so triangles are 180 degrees, rectangles. So what would you think you'd have for a parallelogram?
Well, they're like squares, so would they be a 360?
They'd still be 360 if you've got 4. But you know how you find out? You divide it into a triangle. Because if I cut that there, now I've got triangle, 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 right? Triangle, 3 angles. And when you add these all up, you have 180 plus 180, 360. So just want to show you one thing, though. Don't do this and make 4 triangles and say, oh, there must be 720 degrees. Because we don't want this angle and this angle and this angle. We only want the angles on the outside, see? So let's just run ahead for a second. We'll get this later. What shape is that? How many sides? Pentagon. How many degrees inside a pentagon? If you add it up, this plus this plus this plus this plus this. What's the key? Make a triangle. Okay, so I'm going to make a triangle here, make a triangle here. How many degrees? I'm going to have 180 here, 180 here, 180 here, 540. Okay? So you make the triangles and you got it. That's all. Okay, we've mastered perimeter, and now we're going to study area. People do get them confused. Not people in the real world, because the difference between finding baseboard to go around the room and finding out how much area, how much carpet I need, to me is not confusing. But for people that just do numbers on paper and don't make word problems, it can be confusing. So one little tip might be area. And area is measured in square units, right? Whereas perimeter is measured in linear units, like how many feet long, or how many inches, or how many meters, or how many centimeters. But I came up with that to help those. Maybe that will help you a little bit, because you've got the square and you've got the area. So just remember that area is always measured in square units. So if I say, what's the area of this room? I'm going to estimate. I'm going to say it's 10 feet by 18 feet. So how much carpet would I need? 180 square feet. Now the perimeter would be 10 plus 18 plus 10 plus 18, and we would add that up for linear feet. But square area is square feet, all right? Now, if you want to, we're going to find in this lesson the formula for the area of a rectangle, parallelogram, square, trapezoid, and triangle. When I initially taught math, that was 5 formula. What's the plural of formula? Formulas, formulae, formulae, okay? I'm going to try to condense it and synthesize it till they all stem off of one formula, okay? That's a good thing for you? Now, if you want to learn all 5, go for it. I'm not going to hold you back. I'm just trying to help you, because there's going to be a time when you're going to forget the formula for the area of a trapezoid. I guarantee it. But you might need it. And so what are you going to do? Of course, nowadays you just pick up your iPhone and Google it. But there was a time when you try to have information in your brain. Okay. So what's this shape right here? Rectangle. This is the easiest find the easiest to find the formula for the area because we have the base times the height. Now, why did I draw the height like that? Because it's a cool H. Because the height is always perpendicular. This is critical, especially when you get to parallelogram when the sides are not perpendicular, or a trapezoid. But the height is always perpendicular. So if the base right here was 6 centimeters, and the height, now that wouldn't be centimeters, let's make that 16 centimeters, and let's make the height 10 centimeters, what would be the area of this rectangle? 160 square centimeters, because if you want to think of it this way, there'd be 16 like this, and there'd be 10 like this, and there'd be a grid, and there'd be a whole bunch of little square centimeters in there, right? So 160, how do you write square centimeters? You could either do square centimeters, and you could abbreviate, or you could put centimeters and put a little 2 squared. Either one will work, right? What does this symbol mean if you see that, like feet? 1 slash is feet, 2 slashes it's inches. What if it was an M? Meter. What if it was, okay, you get the idea? All right. So, if you have a rectangle, that's pretty easy. Now let's do the parallelogram. I'm going to make one first for you. Okay, now who was it that liked the lime green? You like the lime green? Okay. You can have this when we're done. How's that? Okay. You have your own lime green parallelogram. How can I make this into a rectangle? Because I want to make all of my formulas base times height, or some form of base times height. Well, what if I was to cut this piece off right here, this little triangle here? I draw a midpoint, draw a line, and I cut it off, and then I put it down here. Would that work? Okay. Now that's pretty good. That's looking like a rectangle. Can do the same thing on the other side. I can cut off the bottom piece and glue it up to the top. How's that? What do I have now? Yeah, it looks like a square, but let's just pretend it's a rectangle for sure. It might be a square, might not. Okay, it's a rectangle. So what's the base? Is the base the same here? Okay, let's say that I start with a base here that is 12 inches. Okay, and let's say I cut off 2 inches here, but then I add 2 inches up here, and then I go over here and I cut off this 2 inches and I put it over here and I add the 2 inches. So when I'm all done, is this shape still 12 inches? Is the base still 12 inches from here to here? Yeah, because where I took away 2, I added 2. And where I took away 2 here, I added 2 over here. So it turns out that the formula for a parallelogram is whatever this base is times what? Where's the height? Is this the height?
No.
Why not? It's not perpendicular. Very good. So the height would be here. Now, I'm just going to tell you, you will get this. I think I've done it in my books, but you'll get it in other people's books too. Let's say that this is 12. They might put that this is 9 and this is 10. We'll make these inches, right? And they'll say, find the area. And what's the area? And kids will put down 120 because they'll say, well, you multiply 12 times 10. That 10 is just thrown in there for perimeter information. You need that information for the perimeter, but this is not for the area. You need the base times the h, the height. Okay, what's 12 times 9? Want to wait? What was it again? Want to wait? That's right. 108 what? Square inches. Very good. Perimeter would just be linear inches. Okay. Okay, now we've done the parallelogram. Now let's do a triangle. Now a triangle, well, I'll do you two. A triangle is either half of a rectangle or it's half of a parallelogram. Regardless of what you do, it's the base times the height times a half. Because you don't want all this, you only want half of it. You don't want this, you only want the base times the height times what? It's a half. Do you see where it's a half? Because it's going to be a half of a parallelogram, it's going to be half of a rectangle. So you could say base times height divided by 2, or 1/2 base times height. They're the same thing. Dividing by 2, taking a half is the same thing. You okay with that? Get energy for one more? You're starting to fade on me. Your blood sugar is dropping. I can see it in your eyes. Okay, here is the next one. It's our old friend El-Zoido. El-Zoido has been captured. He's been trapped. Okay, we got to make a cage for El-Zoido. So how do we make a cage? How big? What's the area of this trapezoid? Let me tell you what the initial way most people teach this. They say base 1, base 2. They say base 1 plus base 2 divided by 2 times the height. Do you like to memorize that? Okay. I like to just say like this, base times height. Wouldn't you? Okay, so here's what we have to do. We have to pull up one of our other little tricky shapes. What shape is this? Trapezoid. I'm going to do my same little routine I did with the parallelogram. I'm going to cut off this little piece here, but I'm going to glue it back on up here. I'm going to cut off this bottom piece here. You have to hold your mouth this way. And then I'm going to glue it back here. What shape is this? Rectangle. Okay, but what's my base here? Just estimate. How many inches? Okay, 11. And what's my base right here? Maybe 8. 7. Okay, we'll say 7. So if this is 7 and this is 11, but when I do my little tricky routine and I pull this out, it's bigger than 7, and I pull this in, it's less than 11, what I'm really finding is this right in here, right, the middle. I'm going to call it the average base. Because if this was 7 and this was 11, what's 7 plus 11? 18. Divided by 2. 9. And that's really what they're doing here. They're adding up 7 plus 11, dividing it by 2. They're finding the average base. They're finding the base from here to here. And this little piece here goes up here. And this little piece here goes up there. And so what we're left with is a base that's in the middle. So in this case, if this is 7 centimeters, this is 11 centimeters. 7 plus 11 is 18 divided by 2. This would be 9. And then our base, our height, I mean, is not this. It's not that. It is perpendicular. Okay? So this is the average base times the height for a parallelogram. That help? So all you have to do is find the average base, multiply by the height, you get the area of a trapezoid, and now El-Zoido is happy. New siding for El-Zoido's house. Okay, now, if you have a protractor, do you have a protractor? Well, if you're watching and you have a protractor, this would be a good time to practice constructing triangles. So I'm going to construct one, but you can do lots of these at home or wherever you are watching this. So what I'm going to do first is I'm going to maybe draw the base, and then maybe I'll go over here and I'll say, let's make this side 75 degrees. And we can go over here and make this side 40 degrees. And then we could connect our points. And we've got this going this way. And we've got this going this way. Okay, it's pretty good. Now, what you're going to figure out after a while is that there's a relationship between the angles. How many angles in a triangle? 3. How many sides in a triangle? 3. This angle right here is 75 degrees. This angle was, what do we make that? Remember?
40.
I forget already. Let's say 40. 40. What would this angle be? 115. 180 minus 115 would be 65. Okay. Now, which side do you think is the longest side up here? Let's do this. Let's do A, B, C. Which side is the longest, do you think? BC. What is the largest angle? And it turns out that you'll see a relationship between the length of a side and the angle, because as I make the angle larger, the side is going to get larger, right? If I made the angle smaller, then this side would be smaller. So what's the smallest side? If this is the longest side here, BC, this would be the smallest because it's opposite the smallest angle. This would be the middle because it's opposite the middle angle, okay? But the 65 and the 75, these look kind of close, don't they? This one and this one, but this is a little bit longer. All right. Now, if you're going to construct some triangles, after a while you might want to start labeling them. If you have a triangle that has 3, what kind of angles are those? Acute angles. This would be an acute triangle, okay? If these were all 60, would that be an acute triangle? Are they all between 0 and 90? Yes, that would be an acute triangle. Okay? What else do you notice about this triangle, though, that's different from this triangle? They're all the same angle. If they have the same angle, what do you know about their side length? They should also be the same. Remember, there's a relationship between the angle and the side opposite. So we would maybe do like this, okay? What do you call a triangle where all the angles are the same? Equiangular. How about if all the sides are the same? Equilateral. Very good. You all knew that? You have that for devotions or something? Okay. The lateral means sides. Quadrilateral means 4 sides. You guys ever lift weights? Who lifts weights here? Do you like to have the big back? You ever see those guys that go, oh, you know, and the big old back muscles? That's called the lats. The latissimus dorsi, I think they're called. So you want big lats, that's sides. Okay, so equilateral is equal sides, equiangular, equal angles. What if you have one like this, that this side and this side and this side are all different? No. This is a hard one. This is one that you're going to hear today and you'll probably never hear it again. Scalene. I wouldn't waste any of my brain corpuscles on that one, okay? Now, you just said another one, though. You said isosceles. How do you spell isosceles? Who wants to help? Help the girl. Spell it. I, very good. We're off to a S, O, S, C, isosceles. Think of isosceles, okay. And it means it's a triangle with 2 sides the same. So it would be 2 sides would be the same, and that would be different, okay. Now, what do you call a triangle that has a right angle in it? A right triangle. That's right. Triangle. Would it be possible to have an isosceles triangle that was also a right triangle? How would you do it? These two would be the same, right? Because this one's not going to be the same, would it? Okay. Keep going. What would be the angle measures of this one? You know that's 90, right? What would these two be? 45 and 45, because the angles had to be the same if the sides opposite of them are the same. Very good. Okay, 45, 45. What do you call these sides here that make the right angle? I'll just tell you now, I think we're going to do it again later. Legs. They're the legs. And they start, leg. And legs make right angles. This is called the hypotenuse. We'll get into that another time. Okay, what do you call a triangle? Well, let me ask you this first. Is it possible to have a triangle with two right angles? Well, let's look. Is that a right angle? Okay, let's put a right angle over here now. Where are they going to meet? Never, right. They're parallel, aren't they? Because if they're two perpendicular to the same side, they're going to go on and on like that. Now, if this one was 89 and this one was 89, eventually they'd meet way up there. But they would meet, but they wouldn't be right angles. So you can only have one right angle, which leads me to this one. What kind of triangle is that? Obtuse. Because it has an obtuse angle and two acute angles. Could you have two obtuse angles in a triangle? No way, because that would be like that, all right? That's if I sat on one of these, go like that. Okay, now you have some blocks near you on the table. I want you to pull out some blocks. Pull out a 5 bar, a 6 bar, and a 7 bar. I'll pull my large wooden blocks out the same. 5, 6, and 7. Or 5, 6, and 8. 8 chocolate, remember? Okay. Connect the inside corners. I mean, these aren't lines because mine are an inch thick, yours are a ½ inch thick, but make a triangle out of those three. Those are your three sides of the triangle. Do 5, 6, and 8. 8, 8. Use the chocolate one, sorry. I changed my mind midstream. Okay, what kind of triangle is it? Well, not quite. It looks like it though, doesn't it? But we can prove it later that it's not. But it looks like a right triangle. What else? What do you know about the angles? Are the angles the same? No. Are they acute angles? Okay, this is acute, this is acute. This might be a little obtuse. This could be an obtuse triangle looking at the angles. Look at the sides. Are they all the same? So it's not equilateral. Are two of them the same? So it's not isosceles. What is it? Scalene. Okay. Now I want you to keep your 8 bar and keep your 5 bar and now pick out your 3. And see if you can make a triangle out of those 3. The 3, the 5, and the 8. What do you think?
Doesn't work.
Oh, that looks like they're all together. Because if I've got the 5 here and I've got the 3 here, to make them touch, that doesn't work. How about if you had a 2? How would that work? So what's this one got to be at least? 4. Okay, try with a 4. Let's try with a 4. Okay. There you go. We're getting a little bit of a triangle. So can you tell me something that you deduce? What do you know about the length of your sides and the kind of a triangle you could make?
The 2 smaller sides have to be at least longer than the longest side.
So the 2 smaller sides have to add up to be at least more than the bigger side.
Yeah.
Because if it's 5 plus 3, 8, that didn't make a triangle. And 5 plus 2, 7, that didn't work, did it? Right. But 5 plus 4 adds up to more than 8. Ah, that's pretty smart. Now I'm going to confuse you and put it in mathematical terminology. And I think there's supposed to be some less than or equal signs in there somewhere. Okay. Now, what does this tell you? What's the smallest side in these three here? A is less than B, less than or equal to B, which is less than or equal to C, right? So we have to put the equal in here because they could all be the same, couldn't they? We could have A equals B equals C. But this is the smaller, this is smaller, this is, okay, this is the big boy. And then the two smallest have to add up and be more than the biggest. Ah, you see why we do this kind of stuff, though? To confuse you? No. But when you see this, stop and think about it. But this makes more sense to me than that. Okay? So your two smaller sides have to add up. So there are some limitations in your triangles. And I think we have covered it. Good. Okay, Cameron, what was that question you just had for me?
Well, where'd polygon?
Where'd Polly go?
Yeah.
I don't know, but Polly gone. She wanted a cracker, I guess. She went to get a cracker. Okay, we don't know. Polly means many. Gone means angles, many angles. Now, everything we've been dealing with so far, how many angles? 3. How many angles? 4. But what if we had more angles? Then with polygon. This is the general term. Now, you can have shapes that have sides like this. What's that look like? It's like a hungry polygon maybe, or Pac-Man, okay? A geometrical Pac-Man. Because it makes a cave, we call these concave shapes. But if it's got an air hose been inside of it and it blows it out, then it would be called a convex polygon. And everything we're going to be dealing with is convex polygons, all right? So what kind of polygon is this? 5 sides, so penta means 5, 5 angles, pentagon. Okay, how about this one? Hexagon. It's got 6. Hex means 6. Okay, how about this one? I draw it like this. I put 2 here, 2 here. Octagon. It's got 8 sides. Stop sign. Okay, octagon. All right, let's just pick one of these. But before we do, we want to talk about in this lesson regular polygons. I think I'd probably call them special, but they call them regular, so we'll do the same thing. A regular polygon is one that has all the angles the same and all the sides the same. Have you had any before? What's a regular polygon that's a 4-sided shape? A square, because a square has all 4 angles the same, all 4 sides the same. Okay, what kind of triangle would be all the same? Equilateral, which is also equiangular. So you've already had 2 regular polygons. But now let's take one that's got, what do you want? How many do you want? 5 or 6 or 8? You pick. 8. Okay, pick the tough one. You pick the 8. Okay, so we're going to do an 8-sided one. Now, that doesn't look regular to me, but let's assume that it is, okay? If it's regular, what's the measure of each of these angles? I mean, each of these are 60, right? Each of these are 90. What's the measure of each of these? I want you to do some thinking. I can tell you, I know this stuff. I wrote the book. But it was work with me a little bit.
Will we have to do the triangle thing like we did before?
Yeah, you got to first find out how many degrees inside totally. So let's go ahead and see how many triangles we can make. Okay, so let's look at this. A 4-sided shape had 2 triangles, right? This would be sides, triangles. And this is an 8-sided shape. How many triangles are there? 1, 2, 3, 4, 5, 6. Okay. If this is 180, 180, 180, 180, 180, 180, what's 6 times 180? Don't even think about reaching for a calculator. Let's go figure this out. Go ahead, you can calculate it, but don't use a calculator.
1080?
Very good, 1080. If there's how many angles in an 8-sided shape? 8, so divide 8 into 1080, And then you'll know how much each of these angles are. Keep going. 8. Too late, got it. Yes, 135 degrees. And you would guess that, wouldn't you? I mean, does it look like an obtuse angle? I mean, this looks like a cube. This is the right angle. 135 degrees. Very good. You figured it out all by yourself. Okay, let's do a six-sided now that you're an expert. A six-sided would be a hexagon. A 6 sides. How many triangles? Just look at this and tell me how many triangles you think you're going to be in there. How'd you get 4? It's 2 less, 2 less, 2 less, right? Okay, and it turns out if you make 3 lines, you'll get 4 triangles. What's 4 times 1 AT? Very good, 720. I know these things, okay? So 4 times 180 is 720, but there's 6 angles. What's 6 divided into 720? 120, good job. Okay, so each of these angles are 120 degrees, okay? Now, you can figure out 5, 7, you can even do a decagon. How many sides is that? 10. How about a dodecagon? 12. See? What's a 20agon? I don't know. Make a name up for it. Duodessa. 2 times 10. All right. Let's look at some other things here, though. Because once you've figured out the inside of a regular polygon, you're going to find out something really interesting about the outside. When I say outside, I mean, let's take a triangle. If this is 60, what is that angle right there? 120, because it's supplementary. And if I extend this side, this is 60. What's this one out here? 120. And if I extend this side, what's this? 120. Very good. What's 120 plus 120 plus 120? 360. Let's take a pentagon now. How many triangles? 3. 3 times 180 is 540. Divided by 5, what do you get for each angle? 108. 108. Okay, 108. So what's this going to be right here? What's the exterior angle going to be? Very good. 72, 72, 72, 72, 72. What's 5 times 72? What? 360. Ooh. It looks to me like we've got a pattern emerging. That regardless of how much we have inside, the exterior angles are always going to add up to 360. They add up to 360. Let's just test one more. Square. How much inside? 4 times 90 would be 360. Exterior, 90, 90, 90, 90, 360. Isn't that cool? So regardless of how big each angle gets inside, a larger and a larger shape. So what if I told you, okay, you got to really, I know this is post-lunch syndrome here. It's going to shake your brain a little bit. If I told you that there was a figure, I didn't tell you how many sides it was on it, but I did tell you that the exterior angle added up to 36 degrees. I mean, it was 36 degrees. Every exterior angle was 36 degrees. How many sides on that thing?
10.
How did you get that?
36 times 10 is 360.
36 times 10 is 360. So there must be 10 36s, right, going all the way around there. What has 10 sides? Decagon. Now, what would be the measure of the interior angle, right there? 144, because 144 plus 36 equals 180. Very good. See, so you can use what you know now about exterior angles instead of making triangles and all that kind of stuff. You can just simply go, oh, well, if the exterior is 36, interior must be 144, da, 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 da. Got it? Okay, sharp. Okay, there's one little formula here that I'm going to write. See if it makes sense to you. The number of sides, I'm going to call n. That's the number of sides. N minus 2 times 180 equals total degrees. So if we had a pentagon, how many sides in a pentagon? So you put your 5 here. What's 5 minus 2? 3. Triangles. As all this is saying is if there's 5 sides, you subtract 2. Remember we saw that? You saw that. 4 minus 2, 6, 2, right? So this just says if you've got 5 sides, then you only have 3 triangles, and 3 times 180 is 540, right? We could even make a trickier formula. Let's make it ourselves. This is the first time I've done this. Divided by n, what would that give you? This is on-the-spot inspiration. If you take 540 divided by 5 sides, you'd get the measure of each angle, right? And we could subtract this from 180 to find the measure of each. You see it? Okay, I'll stop. This is going to challenge my drawing skills, this one. Okay, so maybe what we should do is take some of that licorice you have on your tables, and we could, you know, what could we call this? What was your idea for calling this? Math?
Matthew Eat.
Matthew Eat?
Yeah.
Yeah, Matthew See and Matthew Eat. So we could make the blocks maybe like gummies or something. Okay, maybe we have something here. Okay, but this lesson, I'm going to have to draw circles, and circles are harder to draw than quadrilaterals and triangles, but I'll do the best I can. How would you describe a circle to me? Define a circle.
No corners.
No corners? No ending. That could be a line. No corners and no ending. Go on, keep going. Perfectly round. How would you construct a circle that was perfectly round? But you could use a compass, because a compass then would have the same distance, right? So I could plant that in the middle and I could spin it around. Okay, that would work. The distance from the center to the edge. So you could, I have some definitions in the book. You could cut a piece of string and tie it to a pencil and draw a circle. You could use a compass. But you could say it's a set of points an equal distance from the center. How would that be? A set of points, equal distance. I'm going to add on the plane. So if you had a center of the circle and you draw equal distance all the way around. See, I told you I'm going to struggle with this. So what would you call the distance from the center to the edge? That's right. That's the radius. This would be the center. And there's some debate whether the circle is just the set of points or whether the circle is everything inside. But let's say that everything inside, we're going to call this the area of the circle, right? And we're going to call just the edge itself, what do you call it? Could you call it perimeter? Oh, that's right, because circles don't have perimeter, they have circumference. Circumference. Now this should be review. I mean, we've had this in pre-algebra, we've had it in other books, right? So circumference, area, okay? Some of the things now that we're going to talk about are pretty much just vocabulary. And some you'll use, some you won't. So I'm going to start here, draw a new circle, and I'm going to draw a line that intercepts the circle at 2 points. What do we call that? If this was a line segment that stopped right there and stopped right there, that's a chord, C-H-O-R-D, a chord. Now, if that chord happens to go through the center, what's that called? Who said that? Very good. Okay. How do you spell diameter? A. Turns out, I'm pretty sure in Greek that means through. Dia is through. And it's the measure through. I like to think measure through the center. Okay. So the diameter. Now, if the radius is one side and the diameter is both, then the diameter is 2 times as large as the radius. Correct? Okay. And what would you call it if this line that intersected? Now, even though that's kind of a little line there, let's pretend that it's a perfect straight line and a perfectly round circle. If it just hits at one point, what's that called? T. Starts with a T, ends with a T. And tangent line. But a tangent only intersects the circle at one point. Now, if a line goes through at a couple points, that's called a secant. Okay? You may never use that word again. It's like scalene, but we'll learn it anyway. It turns out what's interesting is the tangent where it intersects is always perpendicular to the center. So even if you drew a tangent right over here, you could, wherever that intersects, that is going to be a perpendicular line, which is something we might use later in proofs. Okay, if you just have a piece of the circumference, what's that called? Arc. Arc. That's an arc. Okay? But if it's a piece of the whole area of the circle, what's that called? Sector. This is like vocabulary 101, isn't it? Okay, you can't leave until you can spell all these words and define them. No, I'm just kidding. I don't want you to spend the night here. So, sector, arc. How do you measure arcs and sectors? We'll talk about that in just a minute. I'm going to try now on a 2-dimensional flat surface to draw a 3-dimensional. Ooh, that's a pretty good circle. What's that look like? A bouncing ball. But what it really is, I'm just trying to show some curvature. That's a sphere. A sphere is a 3-dimensional circle. What do we call a stretched circle like this? An oval. What's another word? Ellipse. You know your lips, maybe? I'm sorry, that was a bad one. And when I say they're bad, they're really bad. Okay, so this is ellipse or an oval. This is a sphere. Okay, let's measure, using the center of the circle, an arc. So if I draw a circle and I have the center and I draw an arc, this arc from here to here is the minor arc. It's the smaller arc. This big boy all the way around would be the major arc. See, you deduced that, didn't you? Opposite of minor, major. If this degree right here is, I don't know, let's say it's, what's that look like? This would be 90, guess. Okay, we'll call it 74 just to be different. How's that? We don't want to make them round up all the time to 5s and 10s. 74 degrees. Then what you would say is that the measure of the arc would be 74 degrees, or you could even write that as measure of, let's put an A, B, C. If the measure of angle ABC is 74 degrees, then the measure of AC, or you could put a little arc sign over top of it like that. Okay? The measure of the arc would be 74 degrees because the arc corresponds to the measure of the angle that created the arc if, ready for this? If it starts in the center. But you're going to find something really interesting this next point, and I don't know if you've known this before, and so I'm going to let you figure it out yourself. But first, some more vocabulary words. If I drew a circle and I put a triangle inside of it, we say that the triangle which is inside the circle is what's another word for write? Scribble? It's inscribed. Okay? Because it's inside and it's scribed. But the circle is like circumference, scribed around the triangle. Get it? So the outside one is the circle. It's circumscribed. The triangle is inscribed. Okay? Now let's use this shape to figure something out. Let's look at this arc right here from this angle. I'm going to say that this is a 60, 60, 60 or an equilateral triangle, and this is 60 degrees. I want you to tell me what you think the measure of this arc is from here to here. 120. Now, how did you figure that out? That's very good. You're correct.
I don't remember.
Okay, well, let's just look at the circle. How far, forget this little triangle and angle and stuff. If we had all the way around, how many degrees? 360. Which fraction of the circle do you think it is from here to here to here? We divided the circle up into how many parts? 3 parts. So this should be a 120 and a 120 and a 120. But if this angle is not in the center but on the circle over here, and this is called the intercepted arc, it is going to be half of this. Or this angle, you double it to find the measure of the arc. Very good. 120. Okay? Did you all get that? Now, if this was in here and it was 60 degrees, then this would be 60 degrees. But if it's 60 degrees over here, it's 120. Covers the whole baby. Okay. Man, you guys did well. Either that or I'm wearing you down. Okay. So who said, I heard somebody mumble this, it's all Greek to me. But Greek can be understood if you know how to speak Greek, right? So that's why we're learning the language of geometry, to understand geometry. That is Greek letters, though. And that is perimetros. What's that sound like if it was in English? Perimetros. Perimeter. See, perimeter, that's an R. P's are pronounced R's. Their P is pi, right? You recognize that? And then you have the R's. This is an M, T, S, so perimetros. Okay. So it looks like there's a guy named Jones around 1707 started using the word pi. He's credited with figuring out pi. Now, people have been studying pi since Archimedes and before. I think there was references to pi when they made the pyramid. But we started calling this little constant pi, and we think it's because it was the first letter of the word perimeter, and the perimeter of a circle is the circumference, and so that's maybe where pi came from, okay? But pi can be written as, Euler used it in 1737. So 1700s, we started calling this constant pi. Now this constant is 3.14 da 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 da. I heard one time of a guy that had memorized the first 100 digits in pi. I have more important things to do with my brain, but maybe that was good and it stretched his. But whatever the reason, 3.14 is the decimal. In fractions, we sometimes call it 22/7. But pi is a constant. It has a value. It's a little over 3. Okay? When you find the circumference of a circle, circumference is 2 pi r. But what is 2 times the radius? The diameter. So you could just say it's pi times d, right? Either one will work for finding circumference. So some people say that pi is defined as, if you have c equals pi times d, if you divide both sides by d, you have pi equals circumference divided by d. So you say that pi is found out by taking the circumference of a circle and dividing it by the diameter, and you're going to get 3.14 da 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 da. If you go online, you can find some places where it'll show a circle like this, and it will have, like the diameter is here, and they'll have 3 diameters plus a little bit, and then this circle just rolls around until it's that long, because if you took this line and wrapped it around, that would be the circumference. The first time I remember teaching this in high school, I took off my belt to show the students how long the belt is to go around my waist, okay? They went, wow, okay. But it's important to realize that whatever your diameter is, your belt's going to be at least 3 times as big, right, if you're circular. In our minds, we're all flat, you know, but in reality, we're more circular. Okay, so let's see how we use this to find the area of a circle. The area of a circle is pi times the radius squared. So let's just draw a circumscribed circle. Okay, it's not too bad, a little flat up here. So if we were to put down a little grid through here, and let's call this the radius, and this is a radius, radius, radius. We know that this is about 3. So what we're really saying is that the area of a circle is about 3 of the squares of the radius, right? So this would be the whole square of a radius, right? You getting this? Because radius squared, let me just pull this out. This would be a radius squared, right? And the whole circle would be about like that. So what this formula is telling us, this is a little over 3 of these. Let's see if we can figure that out. Let's take this little piece of pie right here, and if we were to cut this out and move it around a little bit, it might fit right up in there. Then if we take another little chunk, little sector, and put that up in here, that would fill that up. And then if we take another little chunk and we put that in here, we'd be left with a little bit left. And we'd have 3 full r squareds and a fuzz. Because it's 3 and a fuzz r squareds. You getting this picture? Okay. So you find your r squared, and then you multiply it by 3.14. That's the area of a circle. What if somebody gives you a circle and says, I'm not going to give you the radius, I'm going to give you the diameter. So this circle is 10. How would you find the area of this circle? Okay, the diameter is 10. So then the radius would be 5. So you just do 5 squared times pi, right? Pi r squared. You can figure these things out. There's a couple more examples in the book. If the radius is 6 inches, what would be the circumference? You'd first double it, right? Because 2 pi r, so 2r would be 12 times pi. So you could have 12 pi, or if you multiplied that out, it would be 37.68. But if I move away further, I can see it better. I think 37.68. All right, you get the idea. So you understand where pi came from? Where does it come from? Why do we call it pi? Probably the Greek word for perimeter or periphery. It's the same idea. It starts with the letter pi. When I was studying Greek, they told me that it really is pronounced p. P, rho, sigma, tau, upsilon, like that. But we say pi, so we'll say pi. Where do we use circles a lot? I just thought this would be a good place to stick it in here because we're measuring the earth, right? Geometry is the measure of the earth. And one of the ways we measure the earth, if this is the earth, is we have a thing called the equator. And then we have a lot of concentric circles that go all the way up until we get to the North Pole. And we have them going all the way down to the South Pole. And we divide the distance up from here to here in 90 degrees. So this is 0 degrees. And we go down here to 90 degrees. So then we measure, and by the way, this is, what do you call this? It's latitude and longitude. How do you remember which one is which? Well, the distance up from the equator or down from the equator, I like to think of flatitude. because they're flat circles. And so latitude are the ones that go this way, all right? Yes?
I think about it as a ladder. You're climbing up.
Okay, very good. A ladder, because it's got the T's instead of D's, right? So a ladder, you're climbing up. Now, the biggest circle is going to be the equator, correct? Where's the smallest circle going to be? At the poles, south and the North Pole. It'd be this like right here. I could be standing inside of it. Okay, that would be the pole, but the equator would be the largest circle. So if you happen to live down in New Zealand, you start at 0 and you go down. If you happen to live in London, you'd start at 0 and you'd go up, right? I was in England one summer. I was surprised. 10:30 at night, I could still see the horizon. Now, where I live at 40 degrees latitude, it had been dark. But over there, the sun was still up. And there are places that the sun doesn't go down, right? The higher the latitude. There at 51 degrees where I was in London. Okay. Now, that helps us. But if I say I live at 51 degrees, there's a lot of places that 51 degrees, right? All the way around. A lot of the cities in Canada, 51 degrees. How do you pinpoint then which city? Something called what? Longitude. And longitude, I'll draw another separate circle. Greenwich, England is where the meridian, it's where it starts. But then these circles don't get smaller. They're like a beach ball or something. They're all the same length. Okay, they're all a bunch of circles that just kind of spin. And so you start at 0 here and you go 10, 20, 30, 40 west, 10, 20, 30, 40 east. How many do you think there'd be all the way around? Probably 360 maybe. I don't know, 180? I don't even know. Quick, someone Google it. Latitude, which was flat, goes from 0 degrees at the equator to 90 at the North Pole, 90 degrees at the South Pole. Longitude starts at the Greenwich, England, the prime meridian, and it goes to negative 180 or positive 180 degrees in either direction, east or west. Okay, but what you do is you'd say, well, if you live this many degrees north and this many degrees west or east of the central meridian, you can tell right where you are. Now, my iPhone now, I can just push the compass and it'll tell me exactly where I am. And it won't just tell me degrees. It will even get more specific than degrees. It will tell me 39 degrees, 47 minutes, 52 seconds north. How many minutes do you think there are in a degree? How many minutes in an hour? That's a hint. 60, very good. Okay, how many seconds do you think there are in a minute? 60, okay. So you have your degrees. You want to break it down a little bit smaller. You got minutes. Break it down some more. You got seconds, okay? So you can find out how far north you are, how far west you are, and you can, what do they call that? Triangulate all the different things, and they can locate you. We have lots of this now. 20 years ago, if I'd have talked about this, GPSs and global positioning, they wouldn't know what I was talking about. Now we know, right? Okay. Now, we've got one last stretched circle to talk about, and it is called an ellipse. And that's a pretty bad ellipse, but let's just say that's it. The way you draw an ellipse, you remember when you drew a circle, all you do is you take the center, one piece of string, tie it to your pencil, and you go around, right? Here's what you do to draw an ellipse. I wish you'd try this sometime. You don't have any string with you, do you? Okay. What you need is maybe like 2 nails. I'll draw little nails. And then what you do with these nails, oh, you have licorice. Okay, we can make licorice circles. And what you get a piece of a length of string or licorice, and you make it taut by putting your pencil in it. So you hold it at 2 points and you put your pencil, and as your pencil, if you keep it taut, you keep it tight, and you go all the way around, and then over here, the string will be like shorter here but longer here, and then over here. And that would, when you're all done tracing out, you will trace out an ellipse. But you have to have these 2 focus points, these 2 foci right here. These are the key. A circle has one center, and an ellipse has two. How would you use this in real life? You've got to be thinking some of these things, right? What do we have on the wall over there? Foam. Why do we have foam here? Deaden sound. Because my sound, if I have a flat wall there and I say something there, it bounces right directly to you. But when it hits that foam, it starts moving around inside. It goes inside and it goes ping, ting, ting, like that. Turns out that these, you ever seen a Roman amphitheater or ever been to one of these museums where they have these things? That if somebody stands right here, their voice, okay, let's say I'm standing here, someone's standing here, and I talk and the voice goes here, it bounces right back to that focus point. And if I talk here, it goes right to here. And the way they get those wonderful acoustics is because they understood how sound bounces off of these things and where it goes to. Okay? But that little foam thing there is hitting into the foam and then whoop, it's not allowed to come back at us, right? Okay, so how do you find the area of an ellipse? And I think this is interesting, because I've never heard anybody even talk about this, but if you have a grid, and let's say from here to here is 4, and from here to here is 3, and we draw our ellipse through this. Okay. How does this look like? You remember, what was the formula for the area of a circle? Pi r squared. But what's the r squareds? That's like a little quadrant, right? So if this was a circle, what we'd have is, if it was, let's say 3, 3, 3, 3, we go around like that, what we ended up with was 3 of these r squareds, or a little over 3, pi of those little r squareds. Turns out this is kind of like a rectangle, isn't it? And so a rectangle would be 3 times 4, and then you'd have 3 times 4 and 3 times 4. So if you tore this one up and put it in here, you tore this one up and put it up here, you tore this one up and put it down here, and you have a little strip left over, that's what you do. You take 3 times 4 times pi. Now how do you find the 3 and the 4? Well, they got this big, bizarre thing. They call this the major axis. This is the minor axis. And you find the average. So you say the major, 8 divided by 2 is what? 4. Take the minor average. 3 plus 3 is 6 divided by